We started learning integration by partial fractions, and this method is applied on a rational function, and furthermore is called proper rational function, so that we can make use of this technique. So the first step, when we are given a rational function, we're going to check, is this proper? And if it is proper, then we're moving on. If not, we need to long divide. What is a proper rational function? Only if the degree on top is less than the degree at the bottom, then this is a proper rational function. If not, we say we need to use long division to change into a proper rational function before we can make use of this method. And the second, once we have a proper rational function, we're going to look into the denominator. Can I factor this? And I should be able to factor if I plan on using partial fractions. And you're going to factor as far as possible. And the third step, now we're going to look into, we're going to write this function into the sum or difference of partial fractions. So speaking of partial fractions, they look like this. It's constant over linear form. As a proper rational function, the degree on top is 0, the degree at the bottom is 1. And of course, we can have multiplicity, means you can have some kind of power. And also, what if I have irreducible quadratic in the denominator? Then I will have a linear on top to be the degree less than the degree at the bottom. Of course, we can have multiplicity as well. When we say irreducible, means this quadratic function cannot be factored over real numbers. Okay, let's look at one of the examples. And let's write one integral. Try to integrate this function x squared minus x plus 6 over x to the third plus 3x dx. So first thing, we say first step, we got to inspect. It is a proper rational function. Is this a proper rational function? Yes, it is, because the degree on top is 2, at the bottom is 3. So it is a proper rational function. So next step, we're going to look into the denominator. Can I factor x to the third plus 3x? And we immediately notice common factor of x. Once we factor x, I have x squared plus 3 left. And this is called irreducible because I cannot factor x squared plus 3 over real numbers. And from here, we are going to try to apply partial fraction method, and this is what we're going to do. Here is the function, given function. We factor the denominator, and based on the factor of the denominator, I write the sum or difference of a partial fractions. Since I only have 2 factors, so each factor is a denominator. Because this is linear, so constant must be on top as degree less. And because this is irreducible quadratic, therefore bx plus c, linear, is with lower degree on top. And next step, we say it would be nice if I got to know what a, b, and c's are, and that will be the process of combining now. Now we're going to combine these 2 terms. With x times x squared plus 3 as a common factor, on top we have a times x squared plus 3 plus x times bx plus c. And we can simplify some. X squared plus 3, nothing to do at the bottom, just keep it on top. I will distribute a, I have a x squared plus 3a plus bx squared plus cx. And now we can combine like terms. So like terms means the quadratic terms are alike, and we group them together as a plus b x squared. And notice I only have one linear term, which is cx, so I just copy cx. And then finally, I only have one constant term as well, so I have 3a. Now we got to remember where this came from. This came from here. And if I have the same denominator, I better have the same numerator. In what way? In the coefficients of the corresponding terms must be the same. So therefore, look at the x squared term. X squared term, this is a coefficient a plus b, and the coefficient for x squared term is 1. And for linear term, I have a coefficient c here, and for linear term, I have actually negative 1. For constant term, I have 3a. For constant term, I have 6. So we set up equation based on the corresponding coefficients. I will have a plus b equals 1, c equals negative 1, 3a equals 6. And then we solve these equations. And solve this equation, these two, the bottom two, are really easy to see, as c equals negative 1 and a equals 2. Therefore, b must be negative 1. If I know a, b, and c, then I can put it in, replace a with 2, replace b with negative x, and replace c with negative 1. Now I have my integrand looking a little bit different now. Let's look at this. I'm going to shrink this. Okay, make some space. My integrand is carried from here. I should have a over x, which is 2 over x, plus negative x minus 1 over x squared plus 3 to integrate. We know the antiderivative for the first term. The antiderivative for 2 over x is 2 times natural log of x, absolute value of x. And how would you integrate this item? This, we have seen this a few times. We're going to split them into two integrals as negative x over x squared plus 3 and 1 over x squared plus 3 and dx. And let's try to integrate the last two terms. The first term we can integrate by substitution, and we're going to say let u be x squared plus 3, and du is going to be 2x dx. So therefore, this integral can be written as 1 over u negative 1/2 du. The antiderivative is going to be negative 1/2 natural log of u. Negative 1/2 natural log of u. Remember, u was x squared plus 3. And the next, we have minus the antiderivative of 1 over x squared plus 3. And this is actually our x squared plus a squared form, and a is going to be root 3. So the antiderivative is going to be 1 over root 3 inverse tangent of x over root 3 plus c as our final solution.